Good day, my dear student friends. In this video session, let us learn what are the coordinate systems in finite element method, and what do you mean by shape function, and let us derive the shape functions for one-dimensional linear element. Now we'll start with the coordinate systems used in FEM. There are three coordinate systems we are using in FEM, that is global coordinate system, local coordinate system, and natural coordinates. Okay, global coordinate systems are the Cartesian system of coordinates, and the global coordinate system, it corresponds to a continuum or entire body. Continuum is nothing but a body which is having a series of elements interconnected by means of nodes. Okay, now for example, if you take these global coordinates, they represent the entire system, that is entire structure, entire body. Okay, if you consider the stepped bar, the global coordinate is x only, that is x, because if you consider the entire stepped bar, each node is having a freedom to displace only in x direction only due to the applied load. Okay, now if I consider the 2-bar truss, that is the 2-bar truss, the truss is a combination of here 2 bars, here the global coordinates, if you use the entire structure, if you consider each node is having a freedom to displace in x as well as y direction, hence at each node 2 degrees of freedom globally in this truss case. Likewise, global coordinates for this bar problems we are using x, and for truss problems x and y are the global coordinates. Now come to the local coordinates. Local coordinate system is one that corresponds to a single element. For example, here we have considered the stepped bar. Here I will consider only a single element of this stepped bar. If you consider here also, each node is having a freedom to displace only in x direction. That means at each node 1 degree of freedom in local coordinates also. Okay, if you consider a truss element, truss is nothing but it is a combination of 2 or more bars. For this, in case of 2-bar truss, you take, if you single element, if you consider, that is what local coordinate. What is the local coordinate for this single element of a truss? Local coordinate in case of truss, it passes through the nodes of the single element. That means it is having, let us say, local coordinate for this truss problem is x dash. That means at each node of a truss problem, the local coordinate is x dash, and each node is having 1 degree of freedom locally. Local coordinate. Locally, each node is having only 1 degree of freedom for truss problems. This is what the local coordinate systems. Here we can observe here. Here also, in case of bar problems, the local coordinate system, local coordinate that is x, it passes through the 2 nodes, and here also in case of truss problems also, the x dash is the local coordinate which passes through the 2 nodes, and at each node 1 degree of freedom. Hence in the local coordinates, the bars and trusses are same. You can say bars and trusses are same in local coordinates, that is properties are same for bars and truss in local coordinates only, but in global coordinates they are different. Okay, now come to the natural coordinates. Natural coordinates are the local coordinates whose values does not exceed unity. These are dimensionless numbers. Natural coordinates are dimensionless numbers. They are either 0 or unity. That means they are going to range from 0 to 1. Natural coordinates, they are dimensionless numbers. Okay, these are the natural coordinates. The natural coordinates differ from element to element. If you consider a 1D linear element, the natural coordinate, origin of the natural coordinate, it exists at the center, that is it is 0 at the center, and at node 1 it is going to be, to the left side it is -1, to the right side it is +1. Okay, like this. And for one-dimensional elements, the natural coordinate we are using, that is zeta. For 2-dimensional elements we are using in place of x we are using zeta, and in place of y we are using neta for 2-dimensional elements. Okay, that here it is been shown in the next page. Here you can observe I have considered an example of a two-dimensional element, that is four-noded quadrilateral element, that is four-noded rectangular element. Here you can observe the in this two-dimensional element, it is the origin of the natural coordinate exists at the center, at the interior of this rectangle 0 0. If this is the interior, then the coordinate values of each node will become, at node 1 the coordinate value will become, here since node 1 is to the left of the origin and node 1 is below the origin also, hence it will be -1 -1. Okay, that means this direction represents zeta and this direction represents neta. Okay, from this and node 2 is located to the right of the origin, hence zeta is +1, but it is located below the origin, neta is -1, that is y direction. Next, if you consider node 3, then zeta value, since the node 3 is to the right of the origin, it is +1, and node 3 is above the origin, neta is +1, zeta and neta are +1. And node 4, if you consider, the coordinate values are, the node 4 is located to the left of the origin, zeta is -1, and node 4 is located above the origin, neta is +1. Likewise, you can write the coordinate values zeta, neta for each and every node. These are the natural coordinates. Okay, these are the three coordinate systems we are using in FEM, and also we can derive the shape functions also, and also we can use the words global, local. Like in case of stiffness matrices also, we are using the local stiffness matrix, that is element stiffness matrix, that is for it corresponds to that is local, and global, it corresponds, local corresponds to single element and global corresponds to the entire structure. Okay, now come to the shape functions. Now what do you mean by shape function? Shape function, it is an interpolation function which is used to interpolate the variables at the nodes to the field variable. That means it establishes the relation between the nodal variables and the field variable. That you can write this expression, u is equal to summation of ni ui. What do you mean by this expression? You can, u is equal to summation of ni ui, where ni is the shape function, where ni is the shape function at node I. Okay, now from these shape functions we can deduce the relationship between the field variable and the variables at the nodes. Field variable, that is unknown to us, and ui, these are the variables at the nodes. Like for example, if it is a two noded element, then u1 and u2. Okay, we can develop the relation between u1 and u2 and the field variable, that is the unknown displacement value at any point of the on the element. That means by using the shape functions we can determine the displacement at any point on the element of that particular finite element model. Okay, for example, if you say if you are using three noded element, a single element, then u will be ni ui, that is ni u1 plus n2 u2 plus n3 u3 and so on. If it is a two noded element, then it will be, if it is two noded, then it will be n1 u1 plus n2 u2 and so on. Okay, now let us derive the shape functions. Now let us derive the shape functions for 1D linear element in global coordinates. Okay, that is global coordinate is x for 1D element. Or this derivation also may be expressed in this way also. Derive the linear interpolation polynomial for 1D bar element in global coordinates. Linear interpolation polynomial, we know that u is equal to a1 plus a2x. This is the interpolation polynomial or interpolation function or displacement function for one dimensional linear element, where a1 and a2 are the coefficients of the polynomial, or you can say generalized coordinates. Okay, now to derive the shape functions for one dimensional linear element in global coordinates, let us consider a 1D linear element and its global coordinates is x and the length of the element is le. Let le be the length of the element and node 1 is at a position x1 from the origin, and node 2 is at a position x2 from the origin, and u1 and u2 are the nodal displacements at the nodes 1 and 2 respectively. Okay, now let us assume a displacement model. Already we have discussed in the first module of a finite element method. Okay, that is for one dimensional linear element having two nodes, displacement function can be written as a1 plus a2x. Order of the polynomial will be 1. Okay, a1 plus a2x I have assumed now. Let us assume the displacement model. After that, now you apply the conditions. How do you apply the conditions? We know that at node 1, the position of the node 1 is x1 from the origin, then x is equal to x1, and u will become u1. That means the field variable u will become u1. Then if you substitute this condition into the main equation, then you will get what this is the main equation we have assumed. In this, if you substitute the u is equal to u1, then u1 is equal to a1 plus a2 x1 we will get. Okay, this is the first equation. You just name it as first equation. Now come to the at node 2, apply the second condition. At x is equal to x2 coordinate value, u will become u2. Then if you substitute in the main equation u is equal to a1 plus a2x, it will become u2 plus a1 plus a2x2. Now by solving these two equations, we will get a2 is equal to u2 minus u1 by x2 minus x1. Okay, now substitute the value of a2 in one of these two equations. I will substitute into equation number 1 the a2 value, then we will get a1 value. What is the a1 value we will get by solving? I hope you are following. Now see here, by solving, first we have applied the conditions. X is equal to x1, u is equal to u1. We got the first equation. X is equal to x2, u is equal to u2. If you substitute, we got second equation. Now by solving these two equations, we got a2 is equal to value, and for a2 value, if you substitute in one of the equation, we will get a1. Okay, now a1 we will get u1 x2 minus u2 x1 divided by x2 minus x1. After that, these values of a2 and a1 have to be substituted into the main equation, that is u is equal to a1 plus a2x. Into this equation, if you substitute a1 and a2 value, then we will get the linear interpolation polynomial for 1D linear element. From that we can extract the shape functions. Okay, if we substitute a1 and a2 into the displacement model a1 plus a2x, then if you substitute, then we will get, after solving by rearranging the terms and taking the common of u1 and u2, if you do that, then we will get u is equal to x2 minus x divided by x2 minus x1 into u1 plus x minus x1 divided by x2 minus x1 into u2. In this, here this equation is in this form: u is equal to n1 u1 plus n2 u2. Now I will write this equation in this form: u is equal to n1 u1 plus n2 u2. This is the relationship between the field variable and the variables at the nodes that can be established by the shape functions n1 and n2. Already it is defined. Now from this equation we will come to know that the shape function n1 is given by x2 minus x by x2 minus x1, and shape function n2 at node 2, it is given by x minus x1 by x2 minus x1. These are the two shape functions which we have derived in global coordinates, that is in terms of x for the one dimensional linear element. This is one of the derivation which may be asked in the question paper to derive the shape functions in global coordinates, in terms of global coordinates for one dimensional linear element. Then you should derive these shape functions n1 and n2 in terms of x. Now this is what the one derivation we have covered. Now we will move on to, we will discuss now what are the properties of the shape functions. What are the properties of the shape functions? From this derivation only, by taking this derivation as a reference, we will define the properties of the shape functions. Now, okay, there are three properties of the shape functions we have generally. Now I will consider the same 1D linear element. Here you can observe n1 is 1 at node 1 and n2 is 0 at node 1. n1 is 0 at node 2, but n2 is 1 at node 2. Okay, how it is? Now if you substitute the conditions into these equations n1 and n2 already derived, if you put x is equal to x1 at node 1, we know that at node 1 x is equal to x1. If we put x is equal to x1 in both these equations n1 and n2, then if you put x is equal to x1 in this equation n1 equation, we will get n1 is equal to 1. Okay, n1 is equal to 1 at node 1. And if we put node 1 condition x is equal to x1 into this equation n2 condition, if you put x is equal to x1, then numerator will become 0, then n2 will become 0. n2 is 0 at node 1. Okay, now come to the node 2. At node 2 x is equal to x2. If we put x is equal to x2 in n1 equation, then we will get n1 is 0 at node 2. And if we put x is equal to x2 in n2 equation, we will get n2 is equal to 1 at node 2. That means from this it is concluded that we may conclude that the shape function n1 is unity at node 1, but it is 0 at node 2. n2 is unity at node 2, but it is 0 at node 1. That means the shape function ni is unity at ith node and is 0 at other nodes. For example, let us say for example, if you are considering three noded element, let us say for example, if you are considering three noded element, in this three shape functions will exist for one dimension. Okay, n1, n2, n3. Then here from the first property of the shape function, you can say that n1 is 1 at node 1, but it is 0 at node 2 and 3. n2 is 1 at node 2, but it is 0 at node 1 and 3. n3 is 1 at node 3, but it is 0 at node 2 and node 1. Okay, this is one of the first property of the shape function. Okay, second property of the shape function, what it says? Second property of the shape function, the sum of the shape functions is always unity. The sum of the shape functions for the element, it is always unity. For this one dimensional linear element, if you consider, let us have okay, for this one dimensional linear element, okay, one dimensional linear element n1 plus n2 is equal to 1. The sum of the shape functions is equal to unity. If it is a 3 noded element, n1 plus n2 plus n3 is equal to 1. 4 noded n1 plus n2 plus n3 plus n4 is equal to 1, like that and so on. This is second property of the shape function. We can now verify it. n1 we know for the 1D linear element, just now we have derived x2 minus x by x2 minus x1, plus n2 we have derived x minus x1 by x2 minus x1. If you take the summation of these two shape functions, we will get 1 only. That is, the sum of the shape functions is always unity. Now the third shape function is the derivative of a shape function is constant. That is, if you take the derivative of the shape function with respect to x, it is constant. Derivative of the shape function with respect to y is also the derivative of the shape function n2 with respect to x is also constant. If it is a 2D element, derivative of the shape function with respect to y also it is a constant. How it is? If you take n1, if you take the derivative of n1 with respect to x, it will become constant. n2 with respect to x, the derivative will become constant. This is third property. These are the three properties of the shape functions. That is, the shape the first property of the shape function is ni is 1, ni is unity. The shape function ni is unity at ith node and it is 0 at other nodes. That means n1 is 1 at node 1, n2 is 1 at node 2, n3 is 1 at node 3, and so on. At other nodes, these are zeros. Okay. Second property of the shape function says the sum of the shape functions is equal to unity. That is, it is equal to 1. And third property of the shape function, the derivative of a shape function is a constant. Okay, now in this video session, what we have learned, what are the different coordinate systems used in FEM, that is global coordinate system, local coordinate system, and natural coordinates. And next, shape functions, definition of shape function, and we have derived the shape function for 1D linear element in the global coordinate system, that is in x, in terms of x. And properties of shape functions, we have discussed 3 properties of shape functions. Okay, thank you, my dear students. We will in the next video session we will derive the shape functions for one-dimensional linear element, quadratic element, and cubic element in terms of natural coordinates. Okay, thank you. Take care, stay safe, stay healthy.